Okay, we are solving problem number 1 in homework 9 using the method of undetermined coefficients. So we have our initial differential equation right here. We see that it's not homogeneous, so let's identify this right-hand side as a function of x and call it j of x. Now, we've identified what j of x is. We're going to solve for the homogeneous version of this differential equation and call that solution y sub c, standing for the constant solution. So the operator form, by the way, the operator form of this differential equation will be useful to us later. We're going to call that g of d, and the operator form is d squared minus 3d plus 2 equals 0. So we're going to find the roots of this operator form, and then that's going to correspond to elements in the fundamental solution set of the homogeneous version of this differential equation. So this polynomial factored out is d minus 2 times d minus 1, d equals 1 or 2, so our fundamental solution set for the homogeneous version is e to the x, e to the 2x. That doesn't look right. And I don't care to find it in the code right now, but know that that should be e to the 2x. So yc will be, I just have to fix it right now. There's only like 3 instances of this, so it'll only take a second. And way down here at the bottom. Okay, recompile. Alright, so we know how to build a solution using the fundamental solution set. Yc is c1 e to the x and plus c2 e to the 2x. Now, for the portion of the solution which we haven't found, this is the algorithm, basically. Just follow the steps. Find the annihilator of j of x, call it f of d, quote unquote multiply it with g of d, and the roots of that polynomial correspond to elements in the fundamental solution set of the non-homogeneous version of this differential equation. So the annihilator of x squared e to the x would be d minus 1 to the power of 3. So we'll take that, call it f of d, and multiply with g of d. So d minus 1 to the power of 3 times g of d gives you fsnh. The roots of this polynomial will give you fsnh. So e to the x e to the x squared e to the x cubed e to the x for the repeating d minus 1 4 times, and then e to the 2x. Alright, now we subtract fsh from fsnh, and the elements of this new set, the set resulting from that subtraction, correspond to the particular solution, yp. So, by the way, when we write yp, use alpha or ABC or whatever symbols you're comfortable with to represent the coefficients of your variables in yp, because these are known coefficients. They're not arbitrary constants like they are up here in yc. So we have, I'll use alpha sub 1, 2, 3. So yp equals the solution which corresponds to these elements in a fundamental solution set. Alright, next step, operate g of d on yp and set it equal to j of x. Then combine the like terms that are going to result from that and solve for the non-arbitrary constants alpha 1, alpha 2, and alpha 3. So here's our g of d. Oh goodness, that's not our g of d. That is our g of d, and we're going to operate on yp. So save some space and make it neater to look at, I've factored out e to the x and then taken the second derivative of the coefficient of alpha 1, alpha 2, and alpha 3, added it together, and then subtracted 3 times e to the x times the first derivative of the coefficient of alpha 1, alpha 2, alpha 3, etc., etc., so on and so forth. It's just easier to look at this way. And then at the end I've set it equal to j of x. Alright, now canceling out e to the x, because we have an e to the x, e to the x, e to the x, e to the x here, we can divide by e to the x and simplify it. So this is what our expression looks like after we are done doing those steps. And simplified even further, we see that g of d operated on yp results in this when you set it equal to j of x. This is a system of equations, which fortunately I'm learning about in linear algebra right now. It's pretty easy to deal with. If you can get it into a form like this, perform some row operations, or in this case it's just clearly defined already that by the way, this isn't actually multiplied by x squared. This is just supposed to denote that this row represents the portions of this expression which have an x squared component in them. Probably should have made that more clear, but anyway, and this is the one that corresponds to coefficients which have x components, and this is just constant components. So we have negative 1 alpha 1 plus 2 alpha 2 plus, there's no constant component in this alpha 3, equals 0 because there's no constant component in this right hand side, so on and so forth. So here it's already clearly clearly defined, alpha 3, from there you can solve for alpha 2, and then alpha 1. That's what these are. So you've found your non-arbitrary coefficients of your functions of x and yp. So you know what yp is, definitely. Now you add yp and yc, and that becomes your solution to the differential equation. So in this case, that is what you see here below.